So this also helps us to build complete solutions. So now we have not only IPs, but I mean, we are not only selling IPs, so we can take the example of ARM, for example, but also complete solutions that will address different type of market. This is also shown by the silicon customization. So now there is a need for, again, high computing power. So we have more than GPUs and CPUs. We have now 10 TPUs, sensor, neural, NPUs, etc. for very specific tasks like AI, for example. And last but not least, so supply chain resilience. So we are quite dependent on some foundries, for example. And the fact of having the possibility to, for example, have a chiplet part of your end design that is in a given foundry, let's say, I would say for most geopolitical aspects, but the other one is not in the same. This, depending on which side on the Atlantic Ocean you are in, this can help you get access to I would say, more resilience when it comes to your supply chain. Where does it make sense to have this type of architecture? Mostly autonomous vehicles as of today. So we'll have a connotation on that, so we will maybe not emphasize too much, but automotive is a market where we start to see this SDV approach, software-defined vehicles. We have a lot of, let's say, providers, a lot of different software kit moving around. So it's quite complex to make them work together, say, in harmony. And especially when something is changed, this will bring a lot of additional effort, again, mostly on the software side. So same applies to drones, robotics, and aerospace and defense, where we cannot, let's say, spend, I mean, the time to market for those applications, it's quite long. So if we can save the time that is given by the fact we have access to chiplets, existing chiplets, it is great for those markets, especially since they have strict, let's say, regulations, especially in, I would say, in aerospace and defense, where you need to make sure that this chip behave in a secure way, it's safe, etc. It's proven. DO 254 for those who know. So that's why it's also very interesting to reuse chiplets. Quick messages and statements from our customers, so both accuracy and cadence in this situation. So cost efficiency, that's what I mentioned. We reuse chiplets that are already proven on the market for quite a long time. Time to market, again, we can reuse that. So again, maybe I did not mention it before, but this is due to a new, let's say, paradigm in the, I would say, packaging techniques that help us through, let's say, interposer, redistribution layer to have access to this chiplet architecture. So again, if we start a new project, doing a new SoC on a new node, etc., to some extent we can reuse what was done before, but not completely, especially on the physical design. So this slows down quite a lot the time to market. And I mentioned it before already, so simplified software development. This is true, especially in the case of automotive. So I mean, as of today, what's the journey of a SoC designer and what it will be in the near future? So that's the situation we are in today, monolithic die SoCs. This is great because we can maximize the integration of all of our let's say, hardware modules in a single node. So we maximize the integration in this case. Still, there is a shift toward what we call multi-die SoC, as you can see here, which is basically splitting at least few of the SoC that you have. So this is great especially to maximize the die area. Eventually, if those are in two different technology nodes, and the chiplet. So this is where we have extreme specialization of each and every chiplet that you see here. having this one in the middle that is what we call the system chiplet that will basically be I would say the master of ceremony that will orchestrate all the chiplets around. You will have your CPU that will be a chiplet that you can buy from let's say a third party. Your memory is the same. This AI accelerator, it may be yours or something you buy from a third party as well. And this will be your custom chiplets. So as you can see, being let's say someone that want to build a new product, you can to some extent leverage on quite a significant amount of third-party chiplet, so that you can focus really on where your added value is, and say where you have your secret sauce, I would say. Okay, great. So this is summarized in what we call at Cadence the 4 C's of chiplet. There is one which is for Cadence, right? So cost efficiency, mentioned it already, reduced design time and cost. Customization, so especially when it comes to the, I would say from the low end to the high end devices. So starting with the low end, you can have a chiplet, for example, where you have, I don't know if you can see it, but this is my system chiplet, so the main chiplet that will orchestrate everything. So I can have one CPU, one GPU, let's say one AI modules, accelerator, one memory module. But I can scale it a bit further, having more, let's say, AI accelerators, DSPs, more CPUs or GPUs, keeping the system chiplet, and even more having more CPUs, more GPUs, more AI accelerators. As you can see, we reuse the same system chiplet in this situation. To some extent, you may have two choices. If you can have one system chiplet that is dedicated for low end and mid-range devices, and one for high end, or you can only have one for, let's say, high end that you will reuse even for mid-range or low end. This would maybe you will not use each and every IOs, each and every memory capabilities, but at least this is a way to again be more cost efficient. Configurability, so I guess it's quite the same as customization to some extent. You can remove one chiplet from your package, I would say, and replace it with another. Will it be yours or something coming from a third party again? And Cadence ecosystem. So at Cadence, we are quite involved in this chiplet journey, starting with our partnership with ARM. So defining, maybe you've heard about it, chiplet system architecture, ARM CSA, that I will describe a bit later. UCIe, which is the interconnect connecting two chiplets together within a same system in package. And of course, we have all the EDA tools, all the support that you can provide for you to build your own chiplet. Okay, so this will be the architecture of a unique, I would say, chiplet. So next we will see how it can be built with even more. So as you can see with the color code right here, at Cadence we can provide pretty much all the basic tiles that will be needed for you to build such chiplet, from the bus, the NUC, the AI accelerator, the DSPs, right, from Tensilica. But also, as Secret is being acquired, we have also access to all the safety, security part that is also common to each and every chiplet, because you cannot have one chiplet that is non-secure among all the system in packages. We create quite a backdoor for the attackers. Cadence connectivity IPs, the UCIe, for example, that I mentioned, but also all the standard, let's say, interfaces like Ethernet, USB, etc. And the third-party IPs, so that could be, for example, the ARM IPs that we partner with, but also your own dedicated systems. So that will be what we call the system chiplet. So right here, and this system chiplet will be, as I mentioned, orchestrating everything. So this maximize component reuse, and what we will have here, those CPUs chiplet, and okay, this is just an example, but the AI modules, this will be yours, I would say, or third parties again. So what we have inside the chiplet logic, okay, that's the I would say the secret sauce. The UCIe, that's the interconnect, and for each and every chiplet, as I mentioned, we will have the security, the safety, the debug, because you need to debug each and every chiplet. It's not like an SoC. You need to get access to debug for each chiplet, which can create quite some questions, I would say. And the local control, that is just to, again, the chiplet should be independent so that it should boot on its own, let's say power itself on its own. So this still add a bit of logic. Eventually, you have that in your SoCs, but since you have many chiplets, you will need to bring more, let's say, what we call here local control, and eventually chiplet control. Okay, so this was the long introduction on chiplet. Now I will give you case study on what are the security concerns when it comes to chiplet. So starting with the supply chain. So now we have more and more providers, more and more actors. That may lead to a situation where on our system in package, we lost the control of one of those chiplets that we can call here the victim chiplet. So its integrity, authenticity, whatever has been compromised. This can be done, for example, at the factory where this chiplet was manufactured. It was not manufactured in a, say, factory you should have trusted, I would say. Those factories, or let's say someone injected through some Trojan horse that will impact all the surrounding, and basically interfering with all of your system. So this is not a situation you should encounter in a SoC on which you have the full control, I would say. This is one of the, I would say, issue when you rely on third party, but it comes with the advantages that I mentioned before, of course. So what's the stake with that? So security should be monitored and let's say I would say monitored among all the life cycle of the product, from the manufacturing to the let's say aggregation to the packaging, etc., etc. So what are the constraints still when it comes to security? So we have only one system chiplet with all the IOs. Maybe we lack IOs. It might be limited to some of them. So this can impact the provisioning. So to give you a bit of context on that, provisioning, that's the step where you will inject all the what we call assets, security assets, like the keys that you will use for encryption, for example. And this can pose some issues for provisioning, especially since you will have a lot of steps, additional steps due to the backend. I mean, long backend for chiplet, on which you need to make sure that you inject the keys at the correct time for each and every step. Firmware loading speed. I don't have one SoC. I have multiple chiplets, so they need to boot as fast as one SoC. How to do that? There is the possibility to make what we call a parallel boot, where we'll have one, let's say, primary chiplet, the most trusted chiplet, should be the system chiplet, by the way, that will boot first and then propagate the boot to the other surrounding. If we don't do that, we need to boot chiplet A, then chiplet B, then chiplet C, etc., which for specific use cases like automotive, where the boot time is comes with quite some constraints, it's not very good. Also, this is a consequence as well of having a system chiplet where all the memory are located. Some of them will be flashless, so we don't know. I mean, where to fetch the firmware? It will be from the system chiplet. This creates some problems, I would say, that are solved by the parallel boot, but this is also something to consider when you manipulate those. So I mentioned this notion of trust, hierarchical trust. So we have a primary chiplet. It will manage all the, let's say, trust tasks like attestation, secure boot. I mean, at least the first secure boot. Still, each chiplet will keep its independence, meaning that each chiplet can also attest itself, or maybe rely on the primary the primary chiplet to create what we call a chain of attestation, where the primary chiplet will first attest itself, as it's the most secure, I would say, the most trustable, then create a chain of attestation of its surroundings to make sure that all the package is trusted. Some security requirements just to show you what you should have in this context. So secure by default, this is okay. Well, obvious, right? Owned by default, this is for you to make sure that you don't lose the ownership of what is happening on your chiplet, right? You can't face this situation, because otherwise this may lead to this concern, let's say. So you should do that by monitoring again what is happening on the chiplet all over its life cycle. So trusted ID. Okay. Trusted ID, it's come with the fact of being owned. You need to have a unique identifier per chiplet. Attestation mechanisms, I mentioned that already. Recover from an in-field attack. Again, if one chiplet is compromised, everything might be compromised. So you need to make sure that you can recover without having to, let's say, shut down everything, right? UCIe, so this is the interconnect I mentioned before. You need a way to communicate between those chiplets. So what would be now the minimum function that you should have on each and every chiplet? So each and every chiplet will have security functions. You cannot just have one system chiplet that will do everything. You need to have security on each of them, which is, I would say, good for us, right? As secure IC. So firmware verification, secure boot, trust propagation, key management, because you may still have keys on your chiplet that you don't want the system chiplet or the surrounding to get access to. Attestation, so I mentioned already, I mean, two mechanisms, so TPM, PSA, and IETF. These are, let's say, a standalone attestation. DICE is where you will create the chain of trust I was mentioning before. And what can be the options on top. So PQC, post-quantum cryptography. This is the cryptography that will, say, withstand the quantum computer that is not there, but might be at some point. So there are already algorithms that are standardized for this purpose. And to anticipate, to not redesign everything, etc. This is something you should take care of in advance. PUF, so this is the idea I was mentioning before. So this is a technology we have at SecureIC, on which I guess maybe a third of our 250 patents are on. Anti-tamper, this is again to make sure that you don't protect only one chiplet, but all of them against tampering attacks. And but I guess we will have some talks about automotive right after. Automotive comes with some specific constraints, especially safety. But yeah, I will not mention. Okay. What's the life cycle now? So we have an initial chiplet. We have what we call the chip manufacturer. That is the, okay, I guess the name speaks for itself, for system manufacturer. But now we have a new one, which is the package manufacturer. So this is the actor that will, so AMCOR, let's say, that will package each and every chiplet in a system in package. So we will need to have one master key for this chip manufacturer, one master key for the system manufacturer, that will be you, for example, and the package manufacturer, that will be the end user of this design. So that's where the primary chiplet receives all the firmware, etc. Then deployment. So we have the primary chiplet that is up and running. Now it will propagate all the the certificates, etc., to the other chiplets. Same goes for the attestation that I mentioned before, where we build this chain of trust using dice. In-field updates. So now we have a chip manufacturer, a system manufacturer, and a package manufacturer. They will all have some rights of their own, and they can push some updates. Some will be like loading a new key, loading a new firmware in a secure way, of course. At each and every layer, for example, the chip manufacturer can, for example, modify the first stage of boot. System manufacturer its own stage of boot, and system in package the more higher abstraction layer stage of boot. Keeping edge every time, this is something we have already. Golden image that is there in case there is some failure, so for rollback purposes. And this is my final slide. This is just to emphasize again on the fact that at Cadence, we have all the capabilities to help you build such system. So we're focusing on the ARM chipless system architecture. That is, I would say, the only one right now on the market. On UCAE, which is one of the say standardized interconnects. We have two of them, which are called UCAE and BOW, bunch of wires. All the tools that we have at Cadence, EDA, the IP portfolio, obviously, and the expertise that we have as the chiplet I was presenting before was already taped out last year, September, I guess, in a 3 nanometer node. So this will be a Cadence system chiplet. And it was my last slide. Yeah, thank you.
Thank you. Thank you very much. We've got a couple of minutes for some questions. If there's any questions from the floor. I've got quite a lot about the PKI infrastructure and manufacturing, yeah. But yeah, that's going to take more than a few minutes.
Yeah, I guess it will take more.
Question about UCAE.
Yes.
Is this proprietary? Is this nature?
So this is something we developed with. I guess it's not OCP, but it's something that was developed as part of a consortium with quite a lot of vectors. It's not only for Cadence, so it's not proprietary in that sense.
Is it mature?
It's mature. So as I mentioned, it was taped out already. We have several projects ongoing on chiplet, and this is what we, of course, this is what we push because we were part of it. But this is mature in the sense that it is proven and working in the field. Let's say.
Okay, one more, maybe? Nope. Okay, we'll move on. Thank you very much, Bryce. Thank you.